In today's lecture, we will look at one of the components in the switched mode power converters. We had seen in the earlier lectures that the power converters, in order to efficiently process power, consist of components which do not dissipate energy, and these electrical circuit components are switches, inductors, transformers and capacitors. Switches do not dissipate energy because when they are on, the voltage across them is 0, and when they are off, the current through the switches is 0. Inductors store energy, and when they are discharged, they will give back that energy. Transformers transform power, do not dissipate power. Capacitors, just like inductors, store electrical energy which can be later on recouped. So, all the components that are used in power converters are lossless components. On account of that, the process of power conversion is efficient, and the devices that are used for efficient power conversion are the switches, inductors, transformers and capacitors. So, in this session, we will try to learn the features of switches, what are ideal switches, what are their properties, what are their characteristics, and how these switches are realized with electronic components, and how they are driven, how they are protected, and how they function, how they help in functioning the process of power conversion. A switch is a circuit element. This circuit element has two stable states. Just like other circuit elements, resistor or inductor or capacitor, a switch also has two terminals. It is a two terminal device, but unlike resistors or inductors or capacitors, a switch has two stable states. One state is called the off state and the other state is called the on state. So, we might say that switch is a bistable circuit element which has two terminals and it has two possible states, and in any one of these possible states it can operate stably. These two states are called the off state and the on state. The terminals of the switches are designated as throw and pole. Here I have shown the schematic of a switch in its off state and the switch in its on state. In the off state, the throw T and the pole P are not connected to each other, they are isolated from each other. In the on state, the throw T and the pole P, they are connected to each other electrically. The simple switch that we see here has two terminals and two stable states. The stable states are the off state here and the on state here, and the terminals are designated as a pole and a throw. So, this particular switch has one pole and one throw. So, this is a single pole, single throw switch. In the off state, the pole and throw are isolated from each other. You see, the throw here and the pole here are not electrically connected, and that is the off state of the switch. In the on state, the throw of the switch and the pole of the switch are electrically connected to each other. This is the second state of the switch, the on state. In the off state, the important characteristic of the switch is that the current through the switch is 0. This is the fundamental property of the off state. The current through the switch is 0. We would say that the I off, the off state current in the off state of the switch is 0. There is no current flowing from the throw to the pole or from the pole to the throw. This is the off state, and the most important feature of the off state is that the off state current is 0. In the on state, the throw of the switch and the pole of the switch are electrically connected to each other, and the voltage across the switch is 0. The potential at the pole and the potential at the throw, the electrical potentials, they are both equal, and so the potential difference between the throw and the pole of the switch in the on state is 0. So, we say that in the on state the voltage across the switch is 0. The throw and the pole are both at the same potential. So, in the off state and in the on state, the primary characteristics of a switch are that the current in the off state is 0 and the voltage in the on state is 0. It is very easy to remember the ideal characteristics. Most of the ideal features are 0. In the off state, it is a current through the switch which is 0, and in the on state, it is a voltage across the switch which is 0. But in the off state and in the on state, what happens to the other characteristic of the switch? In any circuit element, we know that there are two circuit variables. One is the current through the element and the other is the voltage across the element. In this particular case, if we consider the off state switch, we know that the off state current through the switch is 0 and the on state voltage across the switch is 0. The question is, what about the off state voltage across the switch and the on state current through the switch? This is the other variable in the electrical circuit quantities. In any electrical circuit, the two quantities that are of importance are the voltage across the circuit element, which will be between the throw and the pole, and the current through the circuit element, which is from throw to the pole or from the pole to the throw. The question is, in the off state, we know that the off state current is 0, but how about the off state voltage? In a similar way, in the on state, we know that the on state voltage is 0, but how about the on state current? Now, the second characteristics of any switch state is related to the circuit in which it is connected. For example, in the off state, the primary characteristics is that the off state current is 0, but in the off state voltage or the voltage across the switch is not 0 and it is determined by the external circuit. For example, in the circuit that is shown here, a battery, a resistor and the switch are all connected in series, and the switch is in the off state, and the two defined quantities are the off state current, and we know that it is 0 because that is the primary characteristics of an off state switch. The off state voltage is marked here, that we do not know by knowing only about the switch, but because it is connected in the circuit and the circuit is known to us, and on account of the fact that the current is 0, it is possible to say that the potential at T will be the same as the potential at this point, the positive plate of the source, because there is no current is flowing in R, and the potential at the pole is the same as the negative terminal of the source, and so the off state voltage in this example is Vg, which is the same as the source voltage. So, what we see here is, in the off state, one of the switch variables, the current through the switch is defined, which is 0, and in the off state, the other variable of the switch, which is the voltage across the switch, is dependent on the circuit in which the switch is connected. In this particular circuit, Vg is the voltage across the switch in the off state. In the same way, in the on state also, the voltage across the switch is defined to be 0, but the current through the switch depends on the external circuit. In this circuit, the same circuit as we had seen before, now the switch is closed. The switch is in the on state. On account of that, a certain amount of current will be flowing. The voltage across the switch is 0 because that is the primary characteristics of the switch in the on state. So, the full voltage Vg will now be across this resistance, and so the current through the circuit is Vg by R, and that is the same current which is flowing through the switch. So, now we see that in the on state, the primary characteristics of the switch, which is the on state voltage, which is 0, but the next characteristics are the on state current is dependent on the source voltage and the load or the external circuit. Now, this particular feature is very important to be noticed, that the switch, which is a bistable element, has two states. State is off state and then the on state. In the off state, the current is 0, and in the on state, the voltage across the switch is 0. The off state voltage is dependent on external circuit, and in the same way on state current is dependent on the external circuit. These are the primary characteristics of any switch, that the current in the off state is 0 and the voltage is divided by external circuit, and the voltage across the switch in the on state is 0 and the current is decided by the external circuit. Okay. Now, any circuit element can also be seen in the VI plane, voltage and current plane, and in a similar way, just like we could plot the voltage and current across a resistor on the VI plane in order to find out the operating points of a resistor, it is possible to see the operating points of the switch for each one of its state. The switch has an off state and an on state, and in the voltage current axis we can plot the operating points of the off state switch. We know that in the off state the current through the switch is 0. So, you will find that the operating point of the switch under the off condition will all be lying along the voltage axis. On the voltage axis current is 0, and that is the characteristics of the off state switch. In a similar way, an on state switch has the voltage across the switch as 0 and any amount of current can be flowing, positive or negative, and you see that the on state operating point of a switch will always be lying on the current axis. The off state switch shown by the red line here will always be on the voltage axis corresponding to 0 current, and the on state operating point of the switch will always be on the current axis, indicating that the voltage across the switch is 0. These are the primary characteristics of the ideal switch. There are a number of other characteristics which we are interested in, and one of them is the power loss. How much power is lost in the ideal switch? The conduction loss relates to the loss when the switch is on, and the blocking loss relates to the loss when the switch is off. In either case, you will find that the power loss in the switch is 0. The conduction loss is 0 because the V on state voltage is 0, and no matter what current is flowing through the switch, the product which represents the power loss is 0. In the same way, in the blocking state of the switch, the current through the switch is always 0. No matter how much voltage the device is blocking, you will find that the product of V off and I off is 0. In an ideal switch, the power loss is 0. In fact, this is one of the reasons why we are using switches for power conversion in an efficient way. Switch was selected to be a component for power converters mainly because in both the states ideally the power loss is 0, and that is what we see here. Okay. What are the other ideal performance characteristics of a switch? Now, a switch has several other operating features. What are those features? How much time does it take to move from one state to another state? The switch has two operating states, the off state and the on state. If you want to switch from an off state to an on state, how much time does it take? And what is the energy involved in moving from one state to the other state? And then how the relative performance of this switch, how the various characteristics of the switch are dependent on the environment conditions like temperature, pressure, altitude and so on. So, these are the performance characteristics of the ideal switch, and we will see that these characteristics also are related to our efficient power conversion. For example, if a switch has to be kept on, to keep it in the on state, the energy required is 0. This is also an ideal characteristics. Real switches may not satisfy this condition. We will see about those things a little later. Energy required to keep the switch in the off state is E off, that is also 0. So, ideally the switch does not dissipate any power, the switch does not require energy to keep it in the on state or to keep it in the off state, and further the time taken to move from one state to the other, off state to on or on state to off, this time is also 0. The time taken to move from off to on or on to off is also 0 in an ideal switch. We will see later that in a real switch all these will be non-zero and will have some minimum requirement as given by the electronic switch that we use or that we employ for carrying out the switching function. While moving from one state to the other state, again some power may be dissipated, but in an ideal switch we will notice that the switch in the off state also has no power dissipation, in the on state also has no power dissipation, while it moves from one state to the other state. At every intermediate point also it has no power dissipation, the time taken is 0. These are all the ideal characteristics of a switch. What I have noted here is energy consumed while moving from off state to on state, or energy consumed while moving from on state to off state is also 0. These are all the ideal performance characteristic of a switch, and these ideal characteristics are totally independent of the ambient conditions. No matter whether the operating temperature is at freezing point or at boiling point or at any other temperature, all these ideal characteristics remain ideal. Since this is an ideal switch, since we also want to set up certain benchmarks against which real switches can be compared, the ideal characteristics are always the best characteristics that one can wish for. Now, what I see here is a compound switch. In many power conversion circuits, a simple on-off switch is not what we use. We use a collection of switches which are put in some combination to achieve a compound switching function. What I show here is a single pole double throw switch. T1 and T2 are the two throws of the switch, and P1 is the single pole of the switch. Such a switch is normally referred to as SPDT, single pole double throw switch. In a similar way, you could have a double pole double throw, triple pole triple throw, triple pole single throw. Many possible combinations of poles and throws are possible, and such switches are compound switches, and in many power conversion circuits we will use compound switches, but these compound switches will be made up of several simple switches. For example, a single pole double throw switch that is shown here is made up of two single pole single throw switches. The poles are connected in common and throws are kept separately, and you will see that a single pole double throw switch can be realized with two single pole single throw switches. In the same way, the simple switches that we have seen, the simple on off switch that we have seen up to now, can be combined in order to get any number of multiple pole multiple throw switches, and in many real applications multiple pole multiple throw switches are quite common. Okay. Now we come to real switches which are used in power conversion. The real switches are electronic switches made up of components, silicon components, which has functions of turning it on, turning off. The control functions are also integrated into the switch function. Such switches are real switches. There are several of them, and we will see them one by one. So, what we see here is the first real characteristics of the switch. What we had seen as the off state current and the on state voltage, which were 0 in the ideal switch, in the non-ideal or in the real switch, both these quantities are non-zero. When the switch is off, some small leakage current will be flowing from throw to the pole or pole to the throw, one way or the other, but some small leakage current will be flowing. This leakage current will not be 0, and this off state current we say is not equal to 0. In a similar way, in a real switch, when the switch is in the on state, the potential of the throw and the potential of the pole are not absolutely equal. On account of that, the voltage across the switch is not 0 in the on state, but it is a small non-zero quantity. This is the first and the fundamental difference between the real switch and an ideal switch. In the off state current is not equal to 0, and in the on state voltage is not equal to 0. Right. The consequence of this non-ideality, the consequence of this feature of real switches results in power loss in the device. Ideally, the power loss has to be 0, but in real switches, we will notice that the conduction loss is the product of on state voltage and on state current, and the blocking loss is the product of off state voltage and off state current. Now, in this real switch, the off state current is not 0, but something which is slightly more than 0. Similarly, the on state voltage is not 0, which is a non-zero quantity. On account of that, both the conduction loss and the blocking loss now will not be 0. On account of that, whether the switch is now in the off state or in the on state, you will find that there is a small amount of power loss in the real switch. This is the first and foremost difference between a real switch and an ideal switch. We can also see the operating points of a real switch in the VI plane. We had earlier seen that the ideal switches show the operating points along the voltage axis for the off state and along the current axis for the on state. But real switches have the characteristics very close to the voltage axis and very close to the current axis, but not exactly on the axis. You will notice that when a switch is on, there is a small amount of voltage drop when the current is flowing through the switch, and similarly when the switch is in the off state, when it is blocking a large amount of voltage, a very small current is flowing. That current is the leakage current, and the voltage when the switch is on is known as the on state voltage. Both these quantities are not 0, and on account of that, you will find that on the VI plane, the real switch operating points will now be close to the axis, but not exactly on the axis. The off state will be very close to the voltage axis, and the on state will be very close to the current axis. And you notice that the characteristic shown here has both sections on the positive current and negative current, positive voltage and the negative voltage. So, this kind of operating on all 4 quadrants, positive voltage, positive current, negative voltage, positive current, and in a similar way bipolar voltage operation and bipolar current operation give rise to an idea of a switch being either a single quadrant switch or a 2 quadrant switch or a 4 quadrant switch and so on. So, what we see here is one of the real switches, a sample real switch, which is a diode. A diode has a characteristics which is shown approximately here in terms of straight lines here, a linearized characteristics. It has a section which is in the 3rd quadrant. For negative voltages, there is a very small negative current flowing, and for positive currents, a very small positive voltage drop is there. The green line that you see here is the on state, and the red line you see here is the off state characteristics. Unlike the ideal switch or the real switch with 4 quadrant capabilities, a diode has characteristics only along the positive current and along the negative voltage directions. The on state of this switch is automatically decided. There are no control features, control possibilities. As a diode turns on or turns off depending on the circuit conditions. There is no control effect that is given to that. The switch is on if the current through that is in the positive direction. The switch is off if the voltage across that is in the negative direction. So, we see that this diode is behaving like an on switch if the current through this diode is greater than 0, and it behaves like an off switch when it is blocking negative voltages. What you see here as a red line is the blocking state, very small leakage current for very large blocking voltages, and what you see here as the green line is the conduction state or the on state, where a very small voltage is dropped for large amount of current that is flowing. The switch has capabilities to pass positive current and block negative voltage. On the current, it is capable of operating only in one direction, positive currents. On the voltage, it is capable of blocking only in one direction, which is negative voltage. So, this diode is defined as a single quadrant switch. It is capable of only passing positive current, blocking negative voltage. We have 4 quadrants of operation relating to blocking capability of positive and negative voltages, passing capability of positive and negative currents. But in this particular case, you see that the diode can pass current only in one direction, block voltage only in one direction. So, this is a single quadrant switch. And another important feature is that in a diode, there are only 2 terminals and there are no control possibilities, and this is an uncontrolled switch. The on state or off state is decided by the external circuit to which this diode is connected. The operating points, as you see here, you could have a conduction state where a large amount of current is flowing with a very small voltage drop, or a very large voltage is blocked with a small current flowing. Now, what I have marked here is the data sheet of one of the diodes. In many of these applications, reading a data sheet or trying to see what are all the data that is given on a switch will help us to understand many features of the switch and many application possibilities of the switch. What you see here is the data sheet of one of the diodes here, which is designated as 20 ETS series, and whenever you see a data sheet, you will see the symbol of the device and you will also see just a small very short description. For example, this device has a forward voltage of about 1 volt at 10 amperes. This is the conduction state. The conduction state is the condition where for a low voltage drop, the device is capable of passing large amount of current. Then what you see at the bottom line here is the reverse blocking voltage. This device is capable of blocking voltages right from 800 volts up to 1600 volts. In this 20 ETS series, there are several diodes. There is a diode which can block 800 volts, and in the same series there will be some other type number which can block 1600 volts. If you see the diode characteristics, the shape of the device is seen here, and you can see that this device is capable of passing an average current, a sinusoidal current with an average value of 20 amperes. It can block a voltage of anywhere between 800 to 1600 volts, and it can take a surge current IFSM, a surge current which is almost 10 to 15 times the rated current. And then you see the on state voltage. When the switch is conducting, the voltage when the current is 10 amperes is about 1 volt, and this is about the environmental condition that the switch is capable of operating anywhere from 40 degrees to 150 degrees. Okay. If you again see a little more on the data sheet on the next page, you will see that the electrical specifications, maximum forward voltage is 1.1 volt at 20 amperes. Normally, this particular line corresponds to the on state of the switch or the conduction state of the switch. When 20 amperes of current is flowing, the voltage drop across the switch is about 1.1 ampere. The bottommost line here that you see here, it says the reverse leakage current when rated voltage is applied. When 800 volts is applied, this will have a reverse current of about 0.1 milliamperes at 25 degrees junction temperature, or 1 milliampere at 150 degrees junction temperature. Now, these are the short features of the diode. As we had seen in the characteristics, the conduction point 1.1 volt at 20 amperes and about 1 milliampere at about 800 volts. These are the important characteristics, and there are a few other things which we will see a little later. So, a data sheet of the devices is a good resource material from which many things one could learn. We will come back to this data sheet a little later. Now, we have seen that in this particular data sheet, the device has a drop of 1.1 volts when passing a current of 20 amperes at a temperature of 25 degrees, and the blocking current is about 0.1 milliamperes at 800 volts at 25 degrees. So, you can see that the loss in the device during conduction and during blocking can be seen here as 22 watts when the device is conducting and 0.8 watts when the device is blocking. Another important thing that we can see, this switch is capable of switching 20 amperes and blocking 800 volts. So, in a way you can say that this switch can switch a power of 20 into 800, which is equal to 16,000 watts. A 16 kilowatts of power can be switched by this switch. That is, you can block a voltage of 800 volts, and under that condition you can switch a current of 20 amperes. So, that is equivalent to a power of 16 kilowatt being controlled, 16,000 watts is being controlled by this diode. But you can see that in relation to 16,000 watts, while the device is on, it drops just about 22 watts, which is less than about or just about 1/10 of 1%. The conduction loss is 1/10 of 1%. So, you can say that this diode is almost as good as an ideal switch. It is controlling a power of 16,000 watts, but the loss inside the switch is just about 22 watts in conduction. But in blocking, that loss is even less. It is about 20 times less than what we had seen before. If the conduction loss was 1/10 of 1%, this is again 1/20th of that. So, roughly the blocking loss in almost all types of switches will be definitely a few orders of magnitude less than the conduction loss. In many cases, blocking loss is invariably totally negligible in comparison with conduction loss. So, we will consider almost all the switches to be almost ideal in blocking and a little less than ideal in conduction. Even in conduction, we see that the dissipation is only 22 watts in comparison with 16,000 watts which is being controlled. So, this type of comparative numbers in terms of losses in comparison with power processed is important, because that is what is going to decide the overall efficiency of the power converter. This is a point which one has to keep in mind. Okay. Now, there is another little feature which one has to see, what I had shown here as the temperature coefficient of the on state. From the data sheet, one can see that at 25 degrees the conduction drop is about 1 volt at 10 amperes, and the same device at 150 degrees junction drops 0.9 volts only at 10 amperes. So, this is a feature which is seen by the fact that as temperature goes up, for the same current the voltage drop falls. This has a very important significance, because if you put several diodes in parallel and try to pass larger amount of currents, supposing I put two 20 ampere diodes in parallel and try to use it for 40 amperes, then this temperature coefficient is an important feature. Because it has a negative temperature coefficient, that is, as the temperature increases, the voltage across the device drops, parallel connected devices will not have stable operating points. For example, if one of the device becomes a little hotter, that device will have a smaller voltage drop. So, it will draw still higher current and it will become even hotter, and eventually one of the devices will fail. Now, this is a feature one has to keep in mind whenever parallel operation is done. Diodes have negative temperature coefficient, and this is an important feature when you wish to operate devices in parallel. This is a very simple application of a diode as a switch. What we have here as the input is an AC source through a transformer given to a secondary, which has a center tap which is connected here, and the two secondary output points are connected through two diodes to a common point and connected to the load. This is normally referred to as the full wave rectifier, single phase input, full wave rectifier. So, the AC quantity which is varying both positive and negative by this rectification action is available to the load as a purely unipolar voltage, and this will have certain average voltage, and that average voltage is what is now across the resistor. So, this application is an AC to DC rectifier, and the rectifier is the generic name for any power converter which converts AC to DC, and this is a simple diode rectifier operating as a single phase full wave rectifier. We have now the second real switch of a whole family of switches. This is another real switch which goes by the name of silicon controlled rectifier, or in short SCR. It has the same symbol as a diode along with a control grid, control gate connected to that. This is a switch which has some control possibilities. It has an anode and a cathode, two terminals just like a diode, which are the power terminals, and it has a pair of control terminals which is the cathode plus the gate. This cathode is a part of power terminal as well as control terminal. Anode is the power terminal, and the gate, which is the third terminal, is a control terminal. The VI characteristics of an SCR has three sections: a one line which is crossing both positive voltage and negative voltage region for very small amount of current, and this particular line is the blocking state of the device, both reverse blocking and forward blocking. This is one stable state of the SCR. SCR also has another name known as thyristor. So, thyristors have one stable state which is the off state. In the off state, it can block positive voltage as well as block negative voltage. So, that is the blocking state, very close to the voltage axis, very small amount of leakage current and a large blocking voltage. The SCR has another state which is the forward conduction state. Current in this can only flow in one direction from the anode to the cathode, which is the positive current. There is no characteristics corresponding to negative current. So, the positive current section has a very low voltage drop. This section of the characteristic is when the operating point is on the very close to the current axis and with very small voltage drop. So, this switch SCR is an on switch for positive currents if it has been gated on. We have a gate terminal here. If a small current is injected into the gate with respect to the cathode, the device will turn on, and once it is on, it is in the on state. In the on state, it has a characteristics which is very close to the current axis. In the off state is when the device has not been triggered on. The gate and the cathode are connected together, or no current flows through the gate and cathode, and the device is in the blocking state. In that state, both positive voltage and negative voltage can be blocked. So, this is an on switch for positive current and an off switch for both positive voltage and negative voltage. So, you can see that this is now a two quadrant switch. It can block both positive and negative voltages, but it can pass only current in one direction. So, it is a two quadrant switch, and this is also called as a semi controlled switch because the control can be only in one direction. You can, by giving a pulse to the gate, you can turn on a thyristor, but you will not be able to turn it off once it is in the on state. So, it can be turned on, but it cannot be turned off. To turn off a thyristor, it is necessary to make the current through the device go to 0, so that the device will regain its blocking characteristics. So, in that way, a thyristor switch or a silicon controlled rectifier is a semi controlled switch. It can be only controlled to turn it on, but you cannot control to turn it off, and it is a two quadrant switch because it can block voltages both positive and negative, but it can pass current only in one direction. Okay. So, what we see here is a data sheet for a thyristor similar to a diode. The thyristor has an on section here and an off section which is both positive and negative, and there is a data sheet which is available for the thyristor. This is made by the semiconductor manufacturer Motorola. It goes by the series name MCR16, and you can see the short feature of this switch. SCRs 16 amperes RMS, 400 to 800 volts. So, this device is capable of blocking voltages anywhere from 400 to 800 depending on the type number in the series. One of the lowest series number will block 400 volts and the highest series number will block up to 800 volts. But all these devices can pass 16 amperes of current, and this is how the package is, the device is packaged. It has A for anode, K for cathode and G for gate. And this tab which you have here is also connected to the anode. We will see a little later about the heat dissipation part. Some of the important specifications are here: blocking voltage up to 800 volts, on state current rating of 16 amperes RMS, high surge current capacity which is almost 10 times the rated current, industry standard package. This kind of package is known as TO220 package, which is a very popular package, and other features are relating to the process which is done. Let us see a few points. For example, this series MCR16D can block 400 volts. MCR16N can block 800 volts. That is what is meant by 400 through 800. In this series, you have three types: MCR16D, MCR16M and MCR16N, and they correspondingly block 400, 600 or 800 volts. And what you see in the next line is the on state RMS current is 16 amperes. It can carry a current whose RMS rating can be as high as 16 amperes, and peak non-repetitive surge current, that is currents which are not repeating continuously, but for one time a large amount of current which is of the order of 10 times the rated current is allowed in such devices. We will come back to this specification a little later. So, what we see here is a two quadrant switch blocking positive and negative voltages, passing positive current, additional feature of control in one direction. Okay. So, from the data sheet it is possible, let us go back to the data sheet and look at one or two of these numbers on the losses. For example, you see that peak on state voltage at a current of 32 amperes is 1.7 volts, and then the peak reverse blocking of 800 volts or whatever is the rated reverse blocking voltage, the current is of the order of 2 milliamperes at 125 degrees and 0.01 milliamperes at 25 degrees. These are the important points. So, if we go to the next one, you can see that conduction loss is now 1.7 volts at 32 amperes corresponding to 54 watts, 2 milliamperes at 400 volts corresponding to 0.8 watts. But the power that can be switched is the product of full voltage and full current, 400 volts and 32 amperes, that is almost 12 kilowatt of power. On 12,000 watts, the dissipation is only 54, which is less than 1/2 of a percentage, less than half of 1/100th, 1/200 times the power that can be transferred through this switch is what is lost in the switch itself during conduction. During blocking it is even less. If 54 watt conduction loss is 1/200 times the full power, the blocking loss is even almost 1/50 times the conduction loss. So, as I said before, the blocking losses are almost always 0. For all switching devices, this is true, that in blocking you might consider that all switches are practically ideal. So, this is an application of a controlled AC to DC rectifier. What we had seen A rectifier is a device which converts AC to DC. The same kind of circuit, the diodes are replaced by thyristor. The load is an inductive load. So, it is possible now because of the gate control that is available, instead of allowing the in the case of a diode, conduction is always at the start of the cycle because diode has no control. But in the case of a thyristor, we can delay the point at which the thyristor is turned on. So, by delaying that, it is possible to get a controlled voltage, which is the output voltage here, and this control angle decides what will be the output voltage. The output voltage can be controlled right from full positive to full negative through the gate control, and this is a controlled AC to DC rectifier. The silicon controlled rectifier in this particular application is working as an AC to DC rectifier with a controlled output voltage. Now, another important point in the data sheet that I wanted to show to you is what is seen here as I square T rating. In all the data sheets of semiconductor devices like diodes and thyristors, you will see one number known as I square T for fusing, and that number is given as about 316 ampere square second, 442 ampere square second for different kinds of conditions. Now, what this particular data is important? It is important for protecting the device. For example, if I wish to protect a diode or protect a thyristor, we had seen that this diode is capable of carrying a surge current of 320 amperes. The thyristor, what we had seen, was capable of having a non-repetitive peak current of 160 amperes. What happens if still larger amount of current flows through the device? The device will get damaged. So, in such conditions, it is necessary to provide protection to the device, and what we show here is a fuse protection. A fuse is connected in series with the device. A fuse is connected in series with the device. Fuse invariably is just a piece of metal which will melt when a large amount of current is flowing through that. By melting and opening, it will protect the device. By using a small inexpensive piece of fuse wire, it is possible to protect the expensive device by using an inexpensive fuse wire. That is the principle of protection here. In such protection, it is necessary to make sure that the I square T rating of the fuse, that is the quantity of the product of square of the current and the time for which the current is flowing, that is what is known as fuse I square T. Whenever a fuse specifies that it has certain I square T, you can take it that when the I square T exceeds that number, the fuse will melt and break. The device I square T is the number which will damage the device. So, if you put both of them in series, if the fuse I square T is less than the device I square T, so even before damage occurs to the device, the fuse will kill itself, will destroy itself, but protect the more expensive power device. That is the principle of protection, and both for the diodes, the I square T numbers which are given are useful for such protection. In the same way, for thyristors also, you will find a number which is known as I square T. Circuit fusing consideration, I square T 106 ampere square second. So, this is the I square T for this device. So long as we use a fuse whose I square T is less than this number, then in a connection like this, the fuse will protect the device. This is the principle of protection for the device. Now, there is another important characteristics which one has to take care of. What we had seen is that these devices ideally should not dissipate any power, but we had seen that the diode was dissipating about 22 watts, 1.1 volts at 20 amperes, or the thyristor was dissipating about 54 watts, which was about, I think, 1.7 volts or so at about 30 amperes current. So, in all these cases, there is a large amount of power dissipation taking place in the device. the power dissipation is not large when compared to the power that is delivered to the load, but it is large in itself compared to the mass of the device, compared to the size of the device. The dissipation that is taking place in the device, a 54 watts in the case of this SCR or 22 watts in the case of this diode, is quite large. So, it is necessary to protect the device against such large power dissipation. The consequence of a large power dissipation is that this large power will get converted into heat on the device, and this heat, if it cannot be carried away, will heat up the junction of the device, and when the junction reaches the maximum limit, the device will get damaged. So, in all these cases, to protect the device from large increase in temperature, junction temperatures, we use what is known as a thermal protection device, or what is known simply as a heat sink. The device is mounted on a large piece of metal, which will carry away the junction heat to itself and then transfer the heat to the ambient over a period of time. So, such thermal protection requires a heat sink to be mounted on the device. The device will transfer its heat to the heat sink will throw the heat to the ambient. In such cases, the data sheets again will tell us some quantity which is known as thermal resistance of the device. For example, let me see this diode. This diode has thermal resistance of junction to case, which is 1.3 degrees per watt. So, what this means is that if 20 watts of power is dissipated in this device, 20 watts into this 1.3 degree centigrade per watt, which is 26 degrees, 20 into 1.3, 26 degrees will be the temperature difference between the case and the junction. So, if you wish to dissipate that kind of power, it is necessary to maintain the case at a temperature which is satisfied by this condition, and for that purpose only we mount it on a heat sink. Now, we can go back to this and see the condition. Supposing if the device is mounted on a case, the thermal resistance of junction to case multiplied by the power dissipation will be the temperature difference between junction and case. This is a mathematical relationship between the junction temperature, case temperature, power dissipated, and also what is the device characteristics, what we had just now seen as 1.3 degree centigrade per watt. This RTH is defined as thermal resistance, P is the power dissipation in the device, theta J is the junction temperature, theta C is the case temperature. If we come to this particular example, where the thermal resistance of the junction to case is 1.3 degree centigrade per watt and power dissipated is 22 watts, and we also know that in this particular case, you can see that the junction temperature can go as high as about 150 degrees centigrade. The maximum junction temperature is 150 degrees centigrade. So, we might like to safely operate the junction at 125 degrees, which is a little 25 degrees less than the maximum. So, in such a case, this relationship tells us that the case temperature should not be more than 96.4 degrees. So, if you mount a piece of heat sink which is capable of maintaining the temperature at or below 96.4, the device will be thermally protected. Later on, we will see a little more about the thermal designs as we get to know about circuit design through examples. Okay. Now, another dynamic performance that one has to take care of is, in the case of diodes, is what is known as the recovery time. The conduction and blocking are the performance relating to steady state, but whenever a device, a diode, moves from an on state to an off state, we notice that this is not an instantaneous process. There is a time required when the positive current comes down to 0 for a duration which is known as reverse recovery time. The device does not block. the device continues to pass current in the opposite direction for a small time. This opposite current flows for a duration known as reverse recovery time, and during that time negative current flows through the device, that is current in the opposite direction to the arrow, flows for a very short duration, which is the reverse recovery time, and during that time some charge storage is taking place in the junction, which is QRR. Now, these properties are again related to the dynamic performance. How long does it take for the diode to recover? From this instant when you have decided to stop the current, the device takes certain amount of time, which is known as reverse recovery time. For example, in this data sheet, which is a fast device, you can see that the recovery takes 65 nanoseconds. That is the time taken for the device to recover. So, this is one of the important characteristics of the device, which one has to remember. As you start using it higher and higher frequencies, this reverse recovery time becomes important, because whenever a device stops conducting, before again it can carry current, you must allow sufficient time for the recovery to take place. And for example, in this particular case, the device recovery is given by, let me see the data sheet. Yeah, the recovery process is shown here with a certain dIF by dt, with a certain slope here and a time. So, these numbers are all given for this device in the data sheet. So, from these given numbers, you can see that when the device recovers, this is a 20 ampere device. Let me see. Yeah, this is a 30 ampere device. So, you can see that during recovery, it passes current in the opposite direction for almost 5 amperes. So, we will stop here now with this session, where we have seen about the ideal and real characteristics of the switches, diodes and SCRs, and some of the dynamic and steady state performances. In the next session, we will continue with the same topic and go on into controlled switches, 4 quadrant switches, and so on. So, that will be in the next session.